Once you've learned to draw Lewis structures, the next step in understanding a molecule is to understand the shape of a molecule. A Lewis structure is going to give you the arrangement of the atoms, the type of bond that you're dealing with, whether or not it's a single, double, or triple covalent bond, and it's going to tell you the location of any unpaired electrons. But a Lewis structure by itself is not going to give you the shape of the molecule. That's where the VSEPR theory comes in. VSEPR stands for valence shell electron pair repulsion theory. Let's break that down. Valence shell means that you're dealing with electrons in the outermost energy level. Electron pair, so those electrons are found in pairs, and then repulsions. Those electrons are trying to get away from one another. So whether or not you're dealing with bonded electrons or non-bonded electron pairs, either way, they are pushing away from each other, and that's going to dictate the shape of the molecule. Here's how we're going to use the VSEPR theory. In the description, you can find some printable versions of VSEPR charts. We're going to be using those charts to analyze a Lewis structure. When you're looking at the Lewis structure, you want to focus on the central atom in the Lewis structure, and you're going to count domains. Domains are just regions of space where electrons are located. A bond is counted as one bonding domain, even if it's a double or a triple bond. A triple bond counts as one bonding domain. A pair of electrons is considered a non-bonding domain. So once you've figured out that information, you go to your VSEPR charts, and the VSEPR charts will help you predict the shape and the bond angle. I do want to point out that the bond angle listed in a VSEPR chart is an approximation. There are some things that affect that. For example, lone pairs tend to change bond angles slightly. So if you have a pair of electrons in the place of a bond, they take up a little more space than a bonded pair of electrons do. So now that we've kind of been over the basics, let's dive into the VSEPR charts and look at some examples. Here you have our first look at a VSEPR chart. Most of your VSEPR charts are going to be arranged in order of total domains. So the simplest case would be 2 domains, and then it would increase from there. You want to be using your VSEPR chart to analyze a Lewis structure. So we'll start by looking at carbon dioxide. Focus on the central atom. Carbon has 2 places where electrons are located on it. It has this double bond right here. That counts as one bonding domain. This double bond also counts as a bonding domain. So there are 2 bonds total. There are no pairs of electrons on the carbon. They would look like this. If you had a pair of electrons on the carbon, that would look like that. But you don't have that in place for the carbon. So there's 2 domains total, no pairs of electrons. Anytime you have that situation, the shape of the molecule is linear. What has happened is that the electrons are spreading out as much as possible. They're pushing away from each other. They're about 180 degrees away from each other to give you that linear shape. The next example is BH3. Focus on the central atom. So look at the boron. There are 3 places where electrons are located. There are 3 total domains in BH3. The boron has no pairs of electrons on it. Even if there were electrons on these outer atoms, we don't count those. We only focus on the central atom. So anytime you have 3 domains, 0 lone pairs, the shape is trigonal planar. All of these atoms are in the same plane, so it's a very flat structure. Trigonal planar is the name of the shape, and by having it in this trigonal planar shape, the bonds are spreading out as much as possible. The next example is the first one that we've seen that has a pair of electrons on the central atom. So there are 3 total domains. Let's look at those 3 domains. This single bond is 1 domain. This double bond is 1 domain. And this pair of electrons is 1 domain. So there's 3 total domains, 1 pair of electrons. So whenever you have that case, the pair of electrons does not really show up in the shape. However, it does contribute to the shape. That pair of electrons is taking up space. These bonded electrons are pushing away from these electrons. That causes the shape of the molecule to be bent. So even though you don't directly see the electrons in this shape, they very much contribute to the shape. And when you draw your Lewis structures, you want to make sure that you've put all of your lone pairs in the correct place, because they are going to contribute to your bond angles and to your shape. Here we are continuing our VSEPR chart, but moving on to 4 domains. The first example we're going to look at is methane, which is CH4. So you have a carbon in the center with 4 hydrogens around it. Focus on the central atom. So you're looking at that carbon. That carbon has 4 bonds around it. That would be 4 total domains. The carbon also has 0 pairs of electrons on it. So there are no non-bonding electrons on the carbon. Anytime you have 4 domains and no lone pairs, the shape is tetrahedral, and a tetrahedral looks like this. Recognize that the tetrahedral shape is very 3-dimensional. These 2 bonds are in the plane of the paper. This one is going back, and this one is coming out towards you. So the tetrahedral shape is very 3-dimensional, allowing the electrons to spread out as much as possible. The next example is ammonia, which is NH3. You have a nitrogen in the center with 3 hydrogens bonded to it and a pair of electrons. So let's count the domains on that nitrogen. Each of the bonds counts as 1 domain. So there's 1, 2, 3 bonding domains, and the pair of electrons also counts as a domain. So there's a total of 4 domains. 1 of them is a lone pair. So the shape is trigonal pyramidal. This trigonal pyramid originated from the tetrahedral. So whenever you've got the total of 4 domains, your parent shape is a tetrahedral, but then a portion of it is missing. This pair of electrons right here is like taking away that bond to give you this trigonal pyramid that you see here. I point that out because I want to make sure that you recognize that this is also a very 3-dimensional shape. If you were to make a model of a trigonal pyramid and set it down on a table, it is going to stand up on the table. It's not going to sit flat the way our planar structure did. It's going to stand up on the table and be very 3-dimensional. By being very 3-dimensional, you are spreading the electrons out as much as possible, which is really the heart of the VSEPR theory. Our last example is water. Water has an oxygen in the center, 2 hydrogens bonded to it, and 2 pairs of electrons on that oxygen. So there's a total of 4 domains, 2 lone pairs on the oxygen. So if you go back to your parent tetrahedral, it's like you took away 2 places. This one is gone and this one is gone, leaving you with a bent shape. So water is a bent structure. I want to spend just a moment introducing a concept called hybridization because it's related to the VSEPR theory. The orbitals within an atom in their normal positions would not be able to get into the bond angles that the VSEPR theory predicts. So scientists believe that these orbitals come together and they hybridize to form new hybrid orbitals that allow for the bond angles that we see within molecules. For example, here is an s orbital and 3 p orbitals. This s orbital and one of those p orbitals come together and hybridize to form 2 sp hybrid orbitals. These sp hybrid orbitals are different shapes from their original orbitals, and they're at different energies. The energy of this new orbital is somewhere in between the energy of the two original orbitals, which is good because originally this orbital had a higher energy. So by coming together and forming these hybrid orbitals, that new hybridized orbital is lower in energy and has a shape that allows for the bond angle that's required for the VSEPR theory. What I've shown you is just one example of a hybrid orbital. There are many others out there, but I wanted to introduce the idea so that we can look at how hybridization relates to bond angles. The type of hybridization present depends on the number of domains. So once again, we're focusing on that central atom and we're counting the domains, the regions of space around the central atom where electrons are located. So for carbon dioxide, there are 2 domains. Anytime there are 2 domains, you're looking at an sp hybridized situation. Sp hybridized will give you a bond angle of 180 degrees. Anytime there are 3 domains, like in the example of BH3, that is sp2 hybridized, and the bond angle should be roughly 120 degrees. When there are 4 domains, it is sp3 hybridized, and the bond angle should be around 109.5 degrees. I do want to point out that these bond angles are approximations. They are most accurate when all of the domains around the central atom are bonding domains. For example, this is methane. Methane has a carbon with 4 bonding domains around it. Those angles are pretty close to 109.5 degrees. Contrast that with ammonia. Ammonia is NH3. The nitrogen has 3 bonded hydrogens and 1 non-bonded pair of electrons. So ammonia still has 4 total domains. It is still sp3 hybridized even though one of those domains is a pair of electrons. However, that pair of electrons takes up more space than those bonds do. So the bond angle is actually a little bit lower than this expected 109.5. The bond angles in ammonia are more like 107.5. So recognize that these bond angles are approximations and that lone pairs will lower the bond angles. That concludes our introduction to the VSEPR theory. Up next, we're going to look at polar covalent bonds.